Hi, everyone. I will present particle methods on the GPU. Here's the introduction. We want to solve some PDEs, for example, the heat equation or other Fokker-Planck equations using particles. And that involves solving a big system of ordinary differential equations of this form. So I might range from 1 to 10 to the 5, maybe. So this is quite a lot of ODEs. And the right-hand side is just some function a that should approximate the gradient of the logarithm of u. The two methods of getting this function a that I'm using in my research are with a neural network, minimizing this loss, and with kernel density approximation using this expression here. So the important parts are the neural network. So there exists a library that supports neural networks and supports GPU programming, which we will see makes it quite easy. And this kind of sum I need to write custom kernels for, which is a little painful, but we will see how it plays out. The goal is to solve the system of ODEs with these two methods on the GPU and make it fast. So let's talk about CUDA.jl. In Julia, which is the language I'm using, CUDA.jl is a package that is like NumPy in Python. It's a wrapper to CUDA in C. Here's an example of what the syntax looks like. So we import CUDA, we import our benchmarking package for timing things. We will be working with an array of size of approximately 1 million. We initialize an array of all ones, we initialize an array of all twos, and we time how long it takes to add them together on the CPU, and it's approximately half a second. Now we initialize the same two arrays, but on the GPU using this CUDA.fill function instead of just fill. And we time how long that takes. It takes about 10 times less time, which is great news. Something to note here is the syntax for adding these two arrays actually did not change. This is thanks to multiple dispatch. I will mention it again. Here's an example of a custom kernel to add two arrays. So we're trying to do the same thing as before, but with a kernel. And this syntax looks very similar to NumPy in Python. So we also need to specify the number of threads and the number of blocks, unlike the previous example where we could just write plus. And this is slower than the array example before, but it is still faster than the CPU implementation. Okay, let's go to the first real example, which is using a neural network. So here, the function called sbtm_fbe is something that I wrote that I'm not showing here that can work both on the CPU and on the GPU. And all it does is it solves that big system of ordinary differential equations. So let's see how it plays out here. We first load this ODE solver. We then initialize the dimension d and the number of particles. So here we just keep it to 10,000, not too high. We initialize the neural network. On the CPU, we sample initial particles on the CPU. Now we need to move everything to the GPU. So we do it here. We move the neural network, the particles, and the time points to the GPU. And now we time the two methods of solving this Fokker-Planck equation, which is just the heat equation, in fact. And we see that using the GPU, it takes 1.2 seconds versus 14 seconds on the CPU. So quite a bit faster. Also, as a sanity check, this computes the maximum of the square of the absolute value, between these two solutions, the GPU solution and the CPU solution. And this is a very small number, implying that it's essentially the same, so everything is correct. The implementation is correct. Again, I'm not showing the implementation here on the slides. And FluxGL, the machine learning library in Julia, it takes care of all of this GPU stuff. So in fact, I needed to change very little code for this to work. Here's another example, which is more complicated. Or here, I'm just showing the timings first. So again, we load the ODE solver, we initialize, so now it's 40,000 particles. We sample the initial particles, we move particles and time points to the GPU, and we solve using the other method, using the blob method as opposed to the SBTM method. So the SBTM method was the neural network approach, and the blob method is the kernel density estimation approach. And here we get approximately the same speed up as we saw in the previous example. Let's see the details of the implementation here, because they're actually interesting. So this is the main difference between the two, the CPU and the GPU implementation. The CPU implementation has this nested loop. So you see that there are several loops, and all of them, and they're all quadratic in n, where n is the number of particles. Whereas the GPU implementation calls these two kernels, and if we look inside these two kernels, each of them has a loop just over n. So each thread loops over all the particles, and there is n threads. And a similar story here. The syntax looks very similar to Numba. And notice that multiple dispatch makes the syntax very nice. So we can call the same function blob underscore score, and just give it different types, array or CUDA array, and it just works. Let's see some benchmarks here. So the y-axis is the time in seconds, and the x-axis is the number of particles. It's log scale. The left is the CPU implementation. So the red line is the neural network. The blue line is the neural network method, and the red line is the kernel density estimation method. We see that the neural network scales approximately linearly with n, and the other method scales approximately quadratically with n. On the GPU, the situation is different. The neural network implementation scales as square root of n approximately, and the kernel density estimation still scales approximately quadratically with n, probably because my kernel implementation is probably not as good as it could be. So this is still future work. Here's another example. I will not go into too much detail here, but this is just another comparison where we obtain a 6x speed up doing something for the Landau equation, another partial differential equation. And this is for 100,000 particles, quite large. So we come to the discussion. Julia makes GPU programming very nice, painless, using this idea of multiple dispatch. I already talked about that. FluxGL and CUDA-GL have really fast prebuilt GPU kernels, which are hard to beat. Custom kernels tend to be slower, but still faster than CPU, so it's still worth it. GPU memory is definitely an issue for me. So on the CPU, I can allocate an n-squared matrix, where n is the number of particles, 10 to the 5. On the GPU, I cannot do that, so I need to do a workaround. I need to allocate an n vector, and each thread loops over n. Also, the upshot is that the GPU parallelization allows me to run much bigger simulations, which is great. This was my original motivation for doing this for my research. Some future work is that I have not used the visual NVIDIA profiler. I want to use it to try to optimize my custom kernels. This is it. Thank you for your attention.